So I just wanted to summarize some work in these articles down here on the questions of causality when it comes to measurements and other operations in quantum field theory. So just to set the scene, the kind of initial question one has is the textbook description of measurement in quantum theory in terms of states, operators, the projection postulate, all the usual stuff, consistent with relativity in the setting of QFT? Now, QFT is a relativistic theory in the sense that it makes accurate predictions in systems where relativity is really relevant. Particles go very fast in colliders, and these predictions usually come from scattering amplitudes and then probabilities in the theory, which are approximations to the real system in the sense that we don't really prepare a state in the infinite past or measure some output state in the infinite future. So then what if we ask more of QFT? Can we just use this textbook description to describe multiple spatially finite and temporally finite measurements in the same background spacetime? Now, one way to do this, you could go down the route of measurement models using, say, unruh DeWitt detectors or other probe quantum fields coupled to the main quantum field. And then you measure the probe systems. And of course, in any model like this, when you trace out the probe system, you will get some update map for the main system of interest. And what I'll be concerned with here are what are the physically possible update maps that could arise from some measurement model like this, or from any measurement model that we could be interested in that we come up with in the future, or really what physical update maps could arise from any physical process. So this is really an operationalist perspective. And we'll be looking for some baseline conditions that any physically realizable or physically reasonable update maps must satisfy in QFT. Now, the usual story in quantum mechanics is that physical operations are described by completely positive update maps. And what we'll see here is that there are some natural additional conditions that arise in the context of QFT. So just the plan for today, I was going to give some quick setup and background before going into talking about the causal operations in Sorkin's original scenario, and then I'll just summarize things quickly in the discussion. So the setup. For simplicity, I'll just be talking about real scalar quantum field theory in some globally hyperbolic spacetime. Just to give you some background info that a lot of you will already be very familiar with, we're going to generate the algebra of observables or of operators with the identity and these smeared field operators, which you can think of as just integrating what's usually called the field operator phi of x against some test function f, test function being a smooth function that's compactly supported in space and time. So for example, with lots of different test functions, f, g, and h here, you could think about their smeared field operators, and you could construct something like this through some complex combinations of them, as well as the identity here. So these are the kind of things that are in our algebra of observables. An important point to note is the commutation relations of two smeared fields. They just give you a C number, the smeared Pauli-Jordan function, smeared over the two test functions f and g in this case. And notably, if the test functions have supports which are space-like, then the Pauli-Jordan function vanishes, and so the smeared field operators commute. And then we will put down some bilinear form on the test functions, W here, which has certain properties, and that will define our 2-point function of our theory. And then we'll be assuming that this is a free Gaussian theory, etc. So this 2-point function will give us all higher endpoint functions. And then we can use the usual GNS construction to represent this on some Hilbert space. And these phi of f, these smeared field operators, will become operators. Sorry, these smeared fields will become operators, and then through things like functional calculus, we can consider functions of these now operators, such as this unitary e to the I phi of f. Okay, so that was just a bit of background, and then to finish off this background section, if you have subregions in your spacetime, we can think about the smeared fields just in those subregions and generate the associated subalgebras. And then this standard condition that comes up in AQFT, Einstein causality, says that for two subalgebras, any elements from those respective algebras must commute. Okay, now I just want to introduce the idea of local operations. So imagine you make a measurement in some local region of spacetime of some observable C local to that region. We can describe this with what I'll call an update map on observables that are not to the past of this region. So what I mean is, if we're given some observable B up here, then when we compute its expectation value, do that not with B, but with EC on B. So like this. And in this way, we can encode the effect of our measurement in the statistics of any future measurements. And I should say as well that this measurement we're thinking about as a non-selective one. So even in the case that we don't condition on any particular outcomes from our measurement, there will still be some effect in this encoded in the statistics of future measurements. We're also thinking of these update maps as acting on the algebra of operators itself, as opposed to an update map on the state. And they must satisfy this unit preserving condition. So just as an example, if you were thinking about ideal or projective measurements, and this operator C was diagonalizable, so you can write it as a sum over eigenvalues and their associated projectors, then the corresponding update map would just look like this whenever you act on any observable B. Now, this may look familiar to people when thinking about the dual picture, where we update the state instead. And in this case, we'd be thinking about trace preserving maps. But we'll be sticking in the dual picture to this, i.e. maps on the algebra itself. Another example is that of a unitary kick. So given some self-adjoint operator C, we can hit B on either side with the associated unitaries for C. And I'll just give this map the symbol U for unitary kick, because I'll just be referring to it later. So we don't need to just be thinking about measurements. In this case, this isn't some sort of measurement. We're thinking about local operations more generally. Now, in the case that B is space-like to C, then space-like commutativity, this Einstein causality, says that C and B commute. And this then ensures what I'll just call the locality of the map. That is, the map will act trivially on B, so it just spits out B again. And you can check this for the two maps that I've shown, the unitary kicks and the ideal measurements. And what this is encoding physically is that expectation values are independent from any operations that are space-like. So measuring an expectation value in here should not depend on any operations that are happening in space-like regions. And remember, we're talking about, in the case of measurements, non-conditional measurements. So we're not thinking about correlations. And then back in the 1970s, Helwig and Krauss laid the foundations to talk about multiple local operations like this. We can have an operation with some operator, either a unitary kick or an ideal measurement, or something else for this region here and its associated update map. Then we'll have another operation for C up here, and it will have its own update map. And we compose them in this particular order because we're in this dual picture involving update maps on the algebra itself. And then for any observable that's not in the past of both of these regions, such as this one here, then when we compute its expectation value, we do it with this composition, EC on B first, and then EA on the result. And then building these update maps from operators, A and C, such as in the case of unitary kicks, will, or because of space-like commutativity, these two update maps will actually commute, and so it won't matter actually which order we've applied them in the case that the two regions are space-like. And that physically makes sense. Okay, so now I just want to talk about, or just give a brief review of Sorkin's scenario or his contribution back in 1993. So consider three agents. I'm working in Dublin at the minute in Ireland, so I'm using these Irish names. We have Aoife in this region over here, and then Caoimhe's acting in this region. And then finally, Biola up here is going to measure some expectation value of their observable B. And we're setting these up specifically so that A and B are space-like. And so in this case, the operators A and B will commute from space-like commutativity, and EA as a map would act trivially on B in this case. It would just spit out B again. Now, the composition rule from before says that when we're computing the expectation value of B, we should do that with this composition of EA and EC. But physically speaking, Biola's expectation value shouldn't depend on any operations that are happening in space-like regions. So this expectation value should just be the same as this right-hand side, which is what you would get if there was no, if EFA was not to act at all. But space-like commutativity, this condition of Einstein causality, won't ensure this in general. It won't ensure this equality. And if we don't have this equality, then we can actually exploit this to get a signal from, or to allow EFA to send a signal from this region down here to Biola up here. But this signal would be, because these two regions are space-like, this signal would be faster than light, which is, of course, a very bad thing. And so we don't want this causality violation in our theory. And this problem is coming about because of Quiva's actions. If Quiva wasn't there, so we don't have this map EC, then both of these two sides would just give us in the end the expectation value of B on its own, and so we would get the equality. So this is Quiva coming in, and their operation is now enabling this superluminal signal. But of course, if Quiva's update map EC is actually describing some real physical process that Quiva can do in this region, then it definitely can't enable such a causality violating dependence of the expectation value up here on operations such as the one down here that are space-like to it. And so Quiva's map, or for Quiva's map, this equality must be satisfied. And so we get this operator equation that says that whenever we're acting on EC on B with some map EA where A is space-like to B, then it must act trivially. The EA must just essentially peel off in this case. And this is a condition on Quiva's map, EC. It's essentially saying that Quiva's map must be such that it won't enable a superluminal signal. Now, I just want to make a comparison to some work that was done in 2001 by Preskill, Beckman, and Gottesman on finite dimensional bipartite Hilbert spaces. In that case, EFA's region would be like part A of the Hilbert space, and Biola's is like part B. And then Quiva's actions are like are analogous to someone coming along and acting on both parts of the Hilbert space. And our question here is analogous to asking if in that bipartite Hilbert space setup, whether or not Quiva's actions would allow someone acting on the first part of the Hilbert space to communicate with someone acting on the second part of the Hilbert space. And what they found there is that if Quiva's actions do allow such a signal from one part A to part B, then those actions can't be implemented faster than the light travel time from part A to part B. Else you would be enabling a superluminal signal, which we don't want. But there's a slight difference in the relativistic setting of QFT in the sense that the space-time locations of any of these actions are baked in. We won't just be saying, we don't have the luxury of saying, well, this action can't be implemented in this shorter time, but it could be implemented in a longer time. Here, because we're putting the space-time locations of these actions into the picture from the get-go, we know how long they take, for example, and how much space they take up. And so any signal in our setup will be superluminal, and so Quiva's map just cannot be implemented at all. Okay, so going back to the QFT setup, one other further point I wanted to make is that this condition on Quiva's update map could be stated even in the case where Quiva's update map is associated to some thickened hypersurface. It's not necessarily local to some compact or bounded region. And this is also analogous to the work by Preskill and Beckman and Gottesman, where they separated out these two ideas of causal operations and local operations. We can talk about the two separately, and I'll summarize that in what follows. So let me just summarize these two ideas of locality and causality, but in the context of QFT. So we're thinking most generally about completely positive unit preserving maps, EC. And then what we have now are these extra natural conditions, this condition of locality that it must act trivially on any operators B that are space-like to the region C. But actually this condition, we essentially get it for free from space-like commutativity or Einstein causality. And then we have this extra condition, this what I was just calling a causality condition, that Cueva's map must also not enable any superluminal signals in this kind of a setup. And here we're assuming as well the locality of the map EA, that it would act trivially on B itself. Now, just to draw a Venn diagram, then in the space of all CP and unit preserving maps, we have those satisfying the first locality condition and those satisfying this second causality condition. And any physically realizable maps must lie in this intersection in here that are both causal and local. And I was able to find a whole bunch of examples in my most recent paper on this subject. So we can talk about unitary kicks of smeared fields, or these weak measurements or Gaussian measurements of smeared fields, and they would be both causal and local. And in fact, there's a whole infinite family of maps that are generalizations of this idea of weak measurements. And then one could also consider the sort of acausal but still local generalizations of these. I've just put in some examples here. Unitary kicks with squares of smeared fields would be local but not causal, for example. And the maps that Chris was talking about in terms of coupling in locally, coupling in probe fields, and then tracing them out, they would be causal and local, so they would be in here as well. And then just to show that this area here is not empty, you can also construct causal but non-local generalizations of these maps. And also, if you want to go further, you could construct maps that were both not causal and not local, but I've not drawn any examples here. Now, a natural condition that arises that's sufficient for causality is what I've just called here the path support non-increasing condition, that roughly speaking is a condition on the map EC that would say that you keep B within its path light cone. So technically speaking, the operator EC on B is localizable in any region down here, such that its future domain of dependence contains the region for B. So the act of keeping B in the path light cone, roughly speaking, like this, is sufficient for this causality condition to be satisfied. And so this path support on increasing subset sits inside the causal one in general. But actually, one of the things that I showed, at least for real scalar quantum field theory, using the properties of the unitary kicks here, you can show that these two conditions are in fact equivalent. So not only does PSNI imply causality, but this causality condition implies PSNI. And so these regions are really the same. Yeah, so that's the summary of the work to date. So what are some, I just want to finish with some open questions / problems. I mentioned ideal measurements at the beginning, but where do they fit in this picture? So given some local observable, we can think about its ideal measurement. It will certainly be a local operator, a local update map, sorry. And we're actually getting evidence to suggest that it's not causal, so it would sit in here somewhere. But then if that is the case, if we're thinking about an operationalist theory of QFT, do we want to think about some sort of reasonable substitute for the projection postulate then, if the usual projection postulate is going to give us acausal operations? I was also only talking about real scalar quantum field theory for a lot of this, and this causality equals path support non-increasing statement was only shown for real scalar quantum field theory. So it would also be nice to see if this generalizes to fermionic field theory and or gauge theory. And then finally, we just started looking at this whole story in the path integral framework. And it would be nice to see if there's anything more that could be learned there, if we can state these causality conditions in maybe an even more natural way. Okay, thank you very much.
Thank you very much, Ian, for your talk. Since it was already a little bit over time, well, let's
Sorry.
see if we can allow. No worry. Let's see if we can allow one quick question. That should be all. Any other questions? You can relate to. You can use Slack as before. Are there any? Okay, yeah, go ahead.
Hey Jan, thanks for the nice talk. So my question would be, is this Sorkin scenario, if you solve it, so if you have a causal operation, does that imply that also superluminal signaling does not appear for higher numbers of combinations of different regions? So I mean, you could imagine like putting 3, 4 or 5 or 6 different regions. Is there, I suppose it's sufficient, but
Yes, yeah, no, that's a great question, because that's something I didn't fit in there. But the path support non-increasing condition is enough to imply that it doesn't matter how many more operations you have down the line, it'll still be causal in the way that you want. Yeah.
okay, thank you.